All right, so for section 10.3, we're going to talk about hypothesis tests for a population mean. So we're going to be using the student's t-distribution again. So as a reminder, t equals x bar minus mu over s divided by the square root of n. And we're going to be using n minus 1 degrees of freedom. So we're going to come back and talk about this more as we progress through. But I want to go through just the kind of general ideas of testing hypotheses regarding a population mean. So we're going to use the classical approach, which means that whenever you have two approaches down here, we're using the one on the left. A couple things we want to talk about here. So to test hypotheses regarding the population mean, we use the following steps, provided that. So we've got to check and make sure that the samples obtained using a simple random sampling or from a randomized experiment, that the sample has no outliers, and the population from which the sample is drawn is normally distributed, or the sample size n is large, so greater than or equal to 30. Also, the sampled values are independent of each other. So whenever we're going through and determining the null and alternative hypotheses, like in section 10.1, then it's going to be structured in one of three ways. So we're going to be talking about a two-tailed test. So if your H1, so your alternative hypothesis is not equal, this will be a two-tailed test. So two-tailed literally means that there's going to be two areas that we're looking at on both ends. So this tail and this tail. So this would be if we have H1 is something like mu does not equal 7. And there's going to be a left-tailed test. So for a left-tailed test, is exactly what it sounds like. So it's where we're looking at the area to the left. So a left tail, that would be shaded. This is going to be our critical region. So these shaded areas are our critical regions. And this would have an alternative hypothesis, or an H1, less than. So maybe mu is less than 7. And for a right-tailed test, again, going to be what it sounds like, where there's going to be the little area over to the right, and again, the H1 might be something like mu is greater than 7. So again, we're looking for that not equal for a two-tail, less than for a left tail, and greater than for a right tail. And this will make more sense as we start to go through it. So we're going to figure out what kind of tail it is. We're going to determine the level of significance depending on alpha. And they're going to give us alpha. Remember that the level of significance, alpha, and the probability of making a type 1 error are all the same thing. We'll end up computing the test statistic. So T naught equals x bar minus mu naught over s divided by square root of n. And again, that's going to follow the student's t-distribution with n minus 1 degrees of freedom. And then we're going to use the table to determine critical values. So this is where we're going to be using our t-table to determine critical values. So the critical values are going to be these lines right here. And so those lines, those critical values, are letting us know where our tails are actually starting, or where that shaded area is actually starting. So as we're going through, if our test statistic falls into the critical region, so this little shaded area, then we're going to reject the null hypothesis. So this is going through and giving that same idea that if our test statistic falls into the critical region, then we're going to reject the null hypothesis. Remember, rejecting the null hypothesis is typically what we want to have happen because it's the alternative hypothesis that's stating there's a change. That's typically what we're interested in. So we would go through all of this and then state our conclusion. And again, I know we mentioned it up top, but this procedure is going to require that the population that we're taking our sample from is normal, or that the sample size is large. All right, so let's actually start talking about this and working through it. So we need to determine our null and alternative hypotheses. We're going to pick an alpha based on the seriousness of a type 1 error. And again, that'll normally be given to us. We're going to compute our test statistics, or our T naught. We're going to determine the critical value or the p-value, and in this case, critical value. We're not going to worry with p-values. We're going to compare the critical value with the test statistic, and then we're going to state our conclusion. And again, here are some nicer pictures of what a two-tail, a left tail, and a right tail test look like. So number one is just asking us to determine the critical value for a right-tailed test with a population mean at the alpha equals 0.01 level of significance with 15 degrees of freedom. So for one, it's telling us it's a right-tailed test. So we have this idea going on. We're going to find out what that value is. So this will be our critical region over here. So we have alpha of 0.01 and 15 degrees of freedom. So in our t distribution, we're going to have an alpha of 0.01 and 15 degrees of freedom. So we're going to come right down and see that it's going to be 2.602. So 2.602 is our critical value. All right, then for B, it's wanting us to determine the critical value for a left-tailed test. So for a left-tailed test, it's going to look like this. And the details are we have an alpha of 0.05 and a sample size of n equals 20. Now remember, degrees of freedom is going to be one less than our sample size. So we're going to go back. So we have alpha of 0.05. We're going to scroll down just a little bit. So 0.05, we had a sample size of 20, which means we have 19 degrees of freedom. So 1.729. 1.729. So I'm going to write down 1.729, but first we need to discuss this. So anything to the left of center is going to be negative. So even though our t distribution table is giving us positive numbers, if we're doing a left-tailed test, then we know that this is actually going to be a negative number. And then for C, we have a two-tailed test. So literally we're going to have two tails, so two parts of it will be shaded. And it's telling us that we have alpha of 0.05. Well, we're actually going to split alpha up. So we're going to take that 5% error and put 2.5% in each tail, or 0.025 in each tail. And it tells us we have a sample size of 13, so that means we're going to have 12 degrees of freedom. So we've got 0.025 is the area in each tail, and then a sample size of 13 means 12 degrees of freedom. So we're going to get 2.179. So 2.179. And then using symmetry, we know that this one's going to be negative 2.179. So we're going to have two critical values for our two-tailed test. And again, these shaded areas, this is representing our alpha. So for B, this was 0.05. And for A, this was 0.01. All right, let's actually start working through a little bit more. So for 12, are women getting taller? In 1990, the mean height of women of 20 years of age or older was 63.7 inches based on data obtained from the Centers for Disease Control and Prevention's Advanced Data Report number 347. Suppose that a random sample of 45 women who are 20 years of age or older today's results in a mean height of 63.9 inches. So it's wanting us to state the appropriate null and alternative hypotheses to assess whether women are taller today. So we're going to start with our H0 and H1. So our H0, so we're talking about the mean here, and it started at 63.7. So the mean is equal to 63.7. And then it's saying that today it's 63.9. So it's wanting us to figure out if women are taller today. So we're trying to see if the mean is taller, if it's increased. So our H1 is going to be that mu is greater than 63.7. Again, we're going to be using mu for both and the same numbers. It's just these symbols in between. your null hypothesis is always equal. And since A is asking us to determine if they're taller, then we're trying to figure out if mu has increased or if it's greater than. That's 63.7. For B, it says, suppose the p-value for this test is 0.35. Explain what this value represents. Now, I know that I said we're going to go through and do the classical approach, but I just want to briefly touch on the p-value idea. So for B, I'm going to draw a picture. So this is going to be a right-tailed test because we have greater than. And this is going to be 0.05. So the area here is 0.05. If it's going through and times the p-value is 0.35, this is referring to the area under the curve. So the p-value is going to be over here somewhere. And it's representing that all this area is 0.35. Well, what we want to look at is where this line is falling in comparison with this one. So if this green line had fallen within this blue area, within the shaded blue area, then we would have rejected the null hypothesis. Or if the p-value had been less than 0.05. So if the p-value was less than 0.05, like if it was 0.02, then it would have been over here somewhere. And this would have been, the area would have been 0.02. But alas, that did not happen. So we have an area over here, so 0.35, whenever our alpha was 0.05. So we are not falling within that critical region, which means we're going to fail to reject the null. So for our conclusion, we're going to fail to reject the null. So there is insufficient evidence that women have gotten taller. All right, so let's go through the entire process. So for 22, reading rate. So Michael Sullivan, son of the author, decided to enroll in a reading course that allegedly increases reading speeds and comprehension. Prior to enrolling in the class, Michael read 198 words per minute. The following data represent the words per minute read for 10 different passages read after the course. So it's because the sample size is small, we must verify that the reading speed is normally distributed and the sample does not contain any outliers. The normal probability box plot is shown. So here, we're looking to make sure we don't have any red dots on the outside of these two curved lines. And then here with our box plot, we're making sure we don't have any asterisks, which we don't. So we can conclude that it's going to be from an approximately normally distributed population. So it's just asking us, B, was the class effective? And it's telling us to use that alpha is 0.10. Well, we're going to have to figure out our hypotheses, so our H0 and our H1. Well, we started out with a reading speed of 198. So that's going to be our null hypothesis, that the mean reading speed equals 198. And we're trying to figure out if this class is useful. So whenever we're talking about our reading speed, for it to be considered useful, we would need to be faster. So greater than 198 words per minute. So now we've got our hypotheses stated. Our general picture, this is going to be a right-tailed test because of the greater than. So we're going to look like so. It tells us that alpha is going to be 0.10. So this area here is going to be 0.10. And now we need to go through and do two things. We need to, one, look up our critical value, and two, compute our test statistic. So we'll do our test statistic first. So the test statistic is T0 equals x bar minus mu naught over s divided by the square root of n. Well, we know n, so we look here, and we have 10 different passages, so n is 10. We don't know anything else. We can get it though. So we are going to use our Casio and calculate all this, or actually have our Casio calculate all this. So we're going to go to Mode, Stat, so number 3. We're going to just use one variable, and we're going to enter in those data points. So we've got 206, 217, 197, 199, 210, 210 again, 197, 212, 227, and 209. So now we've got all 10 in. We're going to click on AC. Then we're going to do Shift, number 1 to get to our Stats menu, and we're looking for the value of X bar and S. So we're going to go to Variable, number 4, and our X bar, number 2, is going to be 208.4. And now we're going to get our standard deviation. So we're going to go Shift 1, still go back to variable. Then our standard deviation is going to be number 4 for a standard deviation of a sample. And that's going to be 9.3832. So now we actually have enough information to go ahead and set this up. So T0 is going to be that 208.4 minus this mu naught. That's going to be the mean that we're using in the hypotheses. So minus that 198 over that 9.3832 divided by the square root of 10. So we're going to have our calculator calculate that for us. So I'm going to go back to mode 1, so we're going to have a nice fraction. So we're going to have 208.4 minus 198 over 9.3832 divided by the square root of 10. And we're going to get 3.505. So it's about equal to 3.505. All right, so we can't actually go ahead and draw this up here yet because we need to find out this critical value. So we have 10, so our n is 10, which means our degrees of freedom is going to be 9, and we have alpha of 0.1. So we're going to go to our t-table. So alpha of 0.1, we had 10 for our sample size, which means 9 degrees of freedom, and we're getting 1.383. So this value here is 1.383, and again, that critical value is coming from the table, from the t-distribution. So this 3.505 is going to fall over here somewhere. So it's going to fall in that critical region, which means we're going to reject the null hypothesis. So our conclusion is going to be that we reject the null hypothesis, so the class worked. So reject H0, so there is sufficient evidence to conclude that the mean reading speed increased. So in short, the class worked. All right, so we just went through and we had something that was significant. So we had data showing that the mean speed increased. But now let's talk about the difference between practical significance and statistical significance. So one of the things to keep in mind is that large sample sizes can lead to results that are statistically significant, while the difference between the statistic and parameter in the null hypothesis is not enough to be considered practically significant. So for our example here, the manufacturer of a daily dietary supplement claims that its product will help people lose weight. The company obtains a random sample of 950 adult males aged 20 to 74 who take the supplement and find their mean weight loss after 8 weeks to be 0.9 pounds with a standard deviation weight loss of 7.2. So it wants us to state the null and alternative hypotheses first. So our null hypothesis and our alternative hypothesis. So the null hypothesis is going to be that the weight loss, the mean weight loss, is nothing. So that the mean weight loss is none. So that this pill would not impact weight loss. And what we're trying to find out is if it is helping the people lose weight. So if the mean weight loss is greater than 0. So if it's helping. So we're going to go through, this is a right-tailed test again. So we'll go ahead and go through the entire process, even though it's not asking us to. So we're going to go through and see that N is 950. It already told us that S, so our standard deviation was 7.2, that our X bar was 0.9. So let's look up our critical value first. So we're going to go to our T-chart. We have 949 degrees of freedom, and it's not giving us an alpha. So let's go with maybe alpha is 0.05. So we'll just determine it. Again, whenever you're being asked to do this, you'll be given an alpha. So we're just going to pick alpha as 0.05. So alpha being 0.05 is going to have us in this column, and we're going to scroll down until we see what's closest to 949. So coming through here, the closest to 949 is going to be 1,000. So we're going to have 1.646. That'll be our critical value, 1.646. So we're going to compute our test statistic and see if it falls into the shaded region. So T naught equals X bar minus mu naught over S divided by the square root of N. So again, I'm just going to put that in the calculator right quick. So we've got X bar, which is that 0.9, minus mu naught, which is 0. So again, that's the number that's going to be in your hypotheses. And we're going to divide that by S, which is 7.2, over the square root of 950. And we're getting 3.853. So indeed, this is going to fall into the critical region. So it's falling into the critical region, which means we're going to reject the null hypothesis. So reject H naught. There's sufficient evidence that the mean has increased. So that implies that it did indeed work. However, this is where the practical significance comes into play. So do you think a mean weight loss of 0.9 pounds is worth the expense and commitment of a daily dietary supplement? In other words, does the weight loss have any practical significance? So again, 0.9 pounds. So this is less than a pound that's lost, and this is over the course of 8 weeks. So really, I don't see anybody really being motivated to lose 1 pound over the course of 2 months almost, and spending that money as following those restrictions. So this would not be practically significant, even though it is statistically significant.